Okay, so welcome back, everybody. So last time I ended with the beginning of the discussion of the next topic that we want to talk about, which is surface integrals. And the beginning, at least, is going to be very similar to how we dealt with line integrals when they were first introduced. So here was the thing I wrote last time, which is just like line integrals were basically like what was the idea? The idea was, a usual Calc 1 integral is an integral along an interval. But what if we took an interval and we deformed it a little bit into a curve instead of, integrating, say, from here to here along this very simple object, we want to integrate along a curve, right? So to do that, our curve C had some parameterization R, and we used that in the definition of our line integral, which was integrating. Eventually, we were interested in integrating a vector field along a curve. But in order to define that, first I talked about the notion of integrating uh, not a vector field along a curve, but just a function along a curve. So we talked about a line integral for a function along a curve, even though what we were ultimately interested in was the line integral of a vector field along a curve. Okay, so the analogy is pretty much the same for surface integral. So we already now, thanks to chapter 14, have the notion of integrating over a 2D region, some function of two or three variables. If we're integrating a function of three variables, we're integrating over a 3D region. Um, and that will come into play later. But for surface integral, the thing that a surface integral is kind of the generalization of is a double integral. So I have the notion of integrating over a two-dimensional region, so that's just a double integral of some function. And the idea here is if I took this, if I imagined this R being like a rug laying on the floor, and I like ruffled it up a little bit so that I got this surface, right? This is still a two-dimensional thing, even though you tend to think of this as sitting in three-dimensional space. You might tend to think about it as a three-dimensional object because it takes three dimensions to represent it, but that's not the case. It's still a surface. It's still a two-dimensional object. And so I want to integrate over this two-dimensional object in the same way that an interval, if I ruffle it up a little bit, it's this curve, right? That, again, you might think of as sitting in two dimensions. It does sit in two dimensions, but it's still a one-dimensional object. So um, anyway, so this surface integral is going to be a notion of integrating over a thing that looks like this. Okay, and so following the analogy here, you might expect that this uses the parameterization now not of a curve, but of the surface. And indeed, that's exactly what this does. Okay, and so we use a parameterized surface here. So we use the notion of a parameterized surface that we developed at the end of chapter 14 stuff to make this a lot more manageable. Okay, so before I move on, I already did a ton of kind of the foundational work with surface integrals, the stuff that kind of takes a big detour um, if you wait until now to cover it, and that is remember that we had this one thing, right, that came into play, but it didn't come into play in too nasty of a way, which is when we first defined line integrals, right? When we talked about the line integral for a function over a curve, the orientation of the curve didn't matter. But when we talked about a line integral of a vector field over a curve, the orientation did matter. Okay, but we saw that that was actually no big deal because the orientation on a curve is either this way or minus this way, right? So talking about orientation on a curve is a very simple thing. That's not really going to be the case for surfaces. It's going to be a little bit more complicated than that. So one thing to note, so note necessarily it turns out that orientation on surfaces is a much messier concept. or I should say is a much messier picture. So you already got a hint of this, right? So in fact, there are some surfaces that are not orientable. So what does orientable mean? Orientable means that you can coherently define an orientation on the whole surface in a way that is coherent in the sense that if I pick a point on the surface and I move along some nice enough path and I traverse the surface, there's some nice, smooth, or continuous way of defining a normal, okay, to the surface at that point. So the orientation of a surface has something to do with how the normal is moving around. Okay, it has something to do with how you can assign a normal at a point on a surface. Okay, so you might recall that when we talked about parametric surfaces. So recall orientation on a surface has something to do with assigning a normal at each point in a, we'll say, consistent way. So there are surfaces that are not orientable, unfortunately. So some of those surfaces are, one example is the Möbius strip. Okay, that I actually constructed a Möbius strip a few lectures ago by cutting out, tearing out a strip of paper and introducing a half turn and then identifying the ends. That gives you the Möbius strip. The Möbius strip is non-orientable, and to see that, you can basically pick a point in the middle of the Möbius strip and think about a person or a thing walking along like the median line of the Möbius strip, trying to keep track of the direction they're facing at every point. Basically what happens is when you get back to where you started, you're facing the opposite direction you should be. One way of talking about what is a problem with these surfaces is that these are one-sided surfaces. They're not two-sided. And it's a problem for wanting to do integrals. And so when it comes to surfaces that we're going to integrate on, we are not going to integrate on these non-orientable surfaces. So our definition of surface integral needs a way of talking about a normal that is consistent. And so we're not going to worry about that. The reason why I talk about it is because it's important to keep track of this stuff, because defining a normal and computing the surface normal is very important to computing surface integrals, because that thing, right, the surface normal we computed back at the end of chapter 14 shows up in our definition of surface integral. Okay, so what is our idea here? So as before, my idea is first define surface integral of function along a surface. Then define surface integral of vector field along a surface. So exactly like we did with line integrals. Okay. So that's the idea. So let's do that. What is our definition of surface integral? So definition of surface integral of function. So surface integral of function. So let sigma be a smooth surface Remember what this means. So sigma is a smooth surface if it has a smooth parameterization. A parameterization is smooth if that weird quantity that came up in computing surface normal from the parameterization is suitably not the zero vector, or if you're talking in terms of length, it's not zero for any of these interior points. So with parameterization, and we'll say this is the smooth parameterization, or a smooth parameterization. So R of uv is x uvi plus y uvj plus z uvk, the typical notation here for parameterized surface. For parameters u and v living in some region R in the UV plane. I'm not going to rewrite this notation again this lecture, so whenever I refer to an R of UV or R of some parameters, this is what I'm talking about. And assume that G is continuous on the surface sigma. Okay, so G is a function. Its domain includes sigma, and G is continuous on sigma. Okay, then the surface integral of G over the surface sigma is the, not that big. This is the, so this is the notation bit. So double integral over sigma is what we use to denote the surface integral. So this is G of x, y, z ds. So this is the surface integral of G over sigma. This is defined to be, so what's on the left here is just notation. This is the double integral over R of G with x, y, and z plugged in. Times, I didn't like that I ran out of room here. Let's rewrite this down here. I didn't like that I ran out of room. I'm gonna have to like insert it. Let's put it over here. Yeah, this is better. So double integral over sigma of G of x, y, z ds. This is defined to be the double integral over R of G of x of uv, y of uv, z of uv. So I'm plugging in the parameterization. And then multiplying this is the length of the vector r sub u of uv cross r sub v of uv dA. There, that's better. Remember where this quantity comes from. Okay, so that quantity is computed. Okay, it is computed in the same way that we computed it when we did this in chapter 14. So in chapter 14, we had computations involving the normal to a parameterized surface, and this quantity shows up, right? It is the length showing up in the denominator, right? If we're talking about the unit normal at a point. Okay. All right, so before we go on and compute any example here, let me do the same thing that I did for line integrals. So here's a fact. You might have the same exact question that you had when we encountered line integrals for the first time, which is what is a surface integral computing, right? So if an integral over a two-dimensional region, right, going back here to my analogy, this double integral over R computed a volume, right? It was the volume of the region bounded above by the graph of f and below by this region R on the xy plane. So this computed a volume before. So what does this compute? Well, similar to how a Calc 1 integral computed an area, but the line integral didn't necessarily, right? It could compute other types of quantities. The surface integral has a very straightforward analogy to the example that I gave you before, which is this. So if sigma we think of being like a thin metal sheet that's a little wavy, okay, or that I've introduced some nice slight curves in. I have some metal sheet that is like slightly corrugated in a nice smooth way, no corners or anything. So if sigma is a thin metal surface, and if G of XYZ is the mass density at any point of sigma. So if we think of sigma sitting in space in front of us, it's some thin metal surface, and we know the mass density function, G of XYZ at any point of sigma, then the surface integral over sigma of the mass density function is the mass of the surface. So this is mass of sigma. Just like if we thought of a thin metal wire, right, being like arranged in space, so it traces out some trajectory in space, the line integral of the mass density function of that wire computed the mass of the wire, right? So this really is like just a two-dimensional generalization of a line integral, right? So surface integral is like a 2D line integral. That is literally what it is. Okay. Now we can show that it actually doesn't matter what parameterization for the surface you use, but it's kind of nasty to do that, so I'm not going to even hint to how that's done. I'm just going to immediately start doing an example here. So the main thing with this is, let me bring back my definition. So when it comes to computing this thing, okay, and of course soon we're going to move on to discuss surface integrals of vector fields, okay, over surfaces instead, which are similar. They're just potentially slightly nastier here. And the big question is, like, how do I actually compute? Where's the problem? Well, just like for line integrals, when you actually plugged everything in and you did all the computations underneath the integral that you had was actually a Calc 1 integral. It was an integral with respect to a single variable, and it was, a Calc 1 integral. So basically there was nothing else to it once you did all of that. The same thing is true here, except it's not a Calc 1 integral. It is a double integral. So these examples are really, really good for if you want to practice your double integration skills, because once you do all of the computation underneath the integral, it's just a double integral in the same sense that all those double integrals you were doing back in chapter 14 stuff. And so it's really efficient if you wanted to study and practice how to do these integrals to actually just focus on examples from chapter 15 stuff. Because after you plug in the parameterization, right, so you're plugging in this parameterization for your surface into G, after you plug that in, and after you compute this weird expression here arising from the normal for the surface, after you compute these two things and you do all of the algebra required to make this look presentable, then you're just doing a double integral, right, in the same way you were doing like a month ago, all right? So that's the deal. So let's do an example. So it's a good first example. Let's evaluate the surface integral of the function e to the z ds, where, so remember this ds is just part of the notation. You're not doing anything extra there. Where sigma is the sphere, x squared plus y squared plus z squared is equal to 9. So that's the sphere of radius 3 centered at the origin in space. Right? Okay. So, what components do I need? Let's quickly go back to our definition. So I need a parameterization for my surface. And then once I have that, I just need to compute all these quantities, right? Okay. So then, let's see. What's a parameterization for this? So let's say I wasn't given a parameterization for this. You just have to come up with this. What's a parameterization for this? What's the idea? What did we do in chapter 14? And so at the end of chapter 14, when we wanted to come up with a parameterization for a surface, kind of our first default thing, especially if the surface is something like part of a sphere, is to use spherical coordinates. It's already like a built-in way of kind of parameterizing these sorts of quantities. So what's the idea? So from spherical coordinates, a parameterization of sigma is what? What was the way we parameterized sigma using spherical coordinates? So r of here, the radius of the sphere is fixed, right? So since the radius of the sphere is fixed, rho is not going to show up as a parameter here because rho is always going to be 3. And so the two parameters that show up here are phi and theta. So our parameterization is going to be in terms of parameters phi and theta. And that is going to be, so it's going to be, since rho is 3 here, the radius is 3, this is going to be 3 sine phi cosine theta I plus 3 sine phi sine theta j plus 3 cosine phi k. And that is for, since it's the entire sphere, phi goes from 0 to pi, and theta goes from 0 to 2 pi. So there's my nice parameterization for my sphere of radius 3 centered at the origin. Okay. All right. So, now what? Well, let us compute what's going on here. All right, let's compute the other quantity that we need. So I need to plug the parameterization into G. That's going to be simple enough here because our G is e to the z. So this is ultimately going to be e to the 3 cosine theta showing up from that. But I also need to compute this bad quantity, which is typically the worst part of these problems, computing this thing here. So let's do that. This is a nice refresher on how this thing is computed. So first I compute r sub phi, phi theta. What is that? So what this is I'm taking the partial derivative of this parameterization with respect to phi. Okay, so the derivative of 3 sine phi cosine theta with respect to phi is 3 cosine phi cosine theta I. In the next slot, with respect to phi, this is also 3 cosine phi sine theta, right? So this is plus 3 cosine phi sine theta, j. And in the last slot, the derivative of 3 cosine phi is minus 3 sine phi. So this is minus 3 sine phi k. All right. Okay. The next one is with respect to theta here. So r sub theta of phi theta is, this is the theta partial of 3 sine phi cosine theta. So this is minus 3 sine phi sine theta I plus 3 sine phi cosine theta j plus 0 k, since this does not depend on theta at all. Okay. Now I need to compute the cross product of these two. So now you see how we're touching on literally every section, every chapter, right, is being touched on here. So let me bring this back. Okay, so there, I want to keep that on screen here. Okay, so let's compute r sub phi cross r sub theta. I'm gonna just make this easier. I'm going to suppress the notation here. Obviously, these depend on both phi and theta, so don't get any wrong ideas. So to compute this cross product, right? So along the top, this is ijk here. Okay, and then in this slot, I have minus 3, or sorry, no, I have 3 cosine phi cosine theta. In the j slot, it looks like I didn't give myself enough room yet again. This is 3 cosine phi sine theta. And in the k slot, this is minus 3 here. Okay, here. Let's redo this. I'll get another piece of paper. Okay, I thought I made it big enough, but I didn't. All right, so this is r sub phi cross r sub theta. So this is, I'll only draw the left one. So this is I, J, K. In the I slot, this is 3 cosine phi cosine theta. In the J slot, this is 3 cosine phi sine theta. And in the K slot, this is minus 3 sine phi. And for r sub theta, this is minus 3 sine phi sine theta. In the J slot, this is 3 sine phi cosine theta. And in the K slot, this is 0. Okay. All right. So now I'm computing this cross product. All right. So how do I do this? Well, let's remember, right, we're treating this like a determinant. That's how we compute the cross product here. So for the I slot, right, I'm doing this, right, and computing the determinant of that 2 by 2 that's left over. Okay, and so this is 0 minus 9 times sine squared phi cosine theta. So this is minus 9. So this is just 9 sine squared phi cosine theta I. Okay. Minus whatever arises here from the J slot. This is going to be 0 times minus minus minus. So again, minus 9 sine squared phi sine theta j. Okay. And then lastly, in the K slot, now I don't get the 0 anymore. This is going to be, so plus 9 sine phi cosine phi cosine squared theta. That's from this multiplication. Minus 9, so that's plus 9 sine phi cosine phi sine squared theta. Okay. Now we can clean this up just a little bit here. So these first two terms, we can't do anything with those yet. This last expression in K, notice that if I factor out a 9 sine phi cosine phi, what I have left behind is cosine squared theta plus sine squared theta, which is 1. So this becomes 9 sine squared phi cosine theta I plus 9 sine squared phi sine theta j plus 9 sine phi cosine phi k. So there is my cross product. Okay. Of course, we're not done yet. All right, so we're not done. What do we do now? Okay, well, now we have to compute the length of this thing. All right, so again, I want to put this at the top. Right here is the thing I'm computing the length of. So I'm computing the length of r sub phi cross r sub theta. So this is square root of 9 sine squared phi cosine theta squared plus 9 sine squared phi sine theta squared plus 9 sine phi cosine phi squared. Okay. So let's think carefully about this for a second. So what do we have going on here? So first of all, I end up with 9. So if I'm going to keep, there's no reason to expand it on this term, so I'm going to rewrite this as, okay, I will. I'll rewrite this as, 81 sine to the 4th phi cosine squared theta plus the second one is 81 times sine to the 4th phi sine squared theta plus 81 sine squared phi cosine squared phi. Okay. And now you see what's going to happen here. So first of all, what I do is I can factor out 81 sine to the 4th phi from the first two terms. And so doing that, I get 81 sine to the 4th phi factored out from the first two terms times cosine squared theta plus sine squared theta. Hey, that's 1, so that's nice. Plus 81 sine squared phi cosine squared phi. Okay. And so this becomes square root of 81 sine to the fourth phi plus 81 sine squared phi cosine squared phi. Now, looks like, maybe if you just look at this for a second, maybe it looks like you're doomed here and nothing is going to come of this. But what if I factor out 81 sine squared phi from both of these things? What do I get? So I get square root of 81 times sine squared phi. And in parentheses here, I get sine squared phi plus cosine squared phi. Oh, we're good, right? We're good. And so this is square root of 81 sine squared phi, which is 9 sine phi. Or, right, the enlightened mind might notice that this is 3 squared sine phi. Curious, right? Why is that curious? I will leave that to you to parse through. All right, but anyway, so this turned out to be 9 sine phi. Okay, so let's go all the way back to the surface integral that we're supposed to be computing, which is the surface integral of e to the z, where this is our parameterization. Now, since this is our parameterization, I will be plugging in 3 cosine phi, which is my z of phi theta function, into e to the z here. Okay, and then I'm going to be multiplying that by this norm that I just found. Okay, and so my surface integral over sigma of e to the z ds is the double integral over the region R. Well, what is the region R here? The region R here is the rectangle in the phi theta plane given by this. Right? So it's a rectangle. I could actually do this in any order I want to. But this is 0 to 2 pi, 0 to pi. This is e to the 3 cosine phi, right, times 9 sine phi. D phi d theta. Okay. All right, so let's compute this now. This shouldn't be too horrible. So, of course, I could actually compute this in any order that I want to. So this doesn't depend on theta at all. So I'm just going to get a factor of 2 pi here, but it doesn't matter. I can do it this way first. So how do I want to do this? So I have e to the 3 cosine phi times 9 sine phi. So if I did this with u sub, if u is 3 cosine phi, then du is going to be minus 3 sine phi. So how am I don't have minus 3 sine phi, I have 9 sine phi. So if I wanted to make this into minus 3 here, this would be 3 minus 3 times. So this would be the integral from 0 to 2 pi of minus 3 e to the 3 cosine phi evaluated from 0 to pi. Okay, d theta. So this would be the integral from 0 to 2 pi of, this would be minus 3e to the 3 cosine pi minus, so plus 3e to the 3 cosine 0. Okay, d theta. There is nothing that depends on theta here, so I'm just going to be end up multiplying by 2 pi. So this is what? This is 2 pi times this is 3e cubed minus 3e to the minus 3. Yeah. All right, that's that surface integral.